So thank you for allowing me to present my work at this conference. So I'll be presenting on, like Yaroslav said, spin-dependent coupling between quantum dots and topological quantum wires. So basically systems that look something like this. And this was done at the University of Basel in collaboration with Denis Chevalier, Elena Klinovaja, and Daniel Loss. So I'll give a brief introduction to kind of Majoranas in quantum wires. So they were kind of theoretically proposed around 2010 by several people, so lots of references. And basically the necessary ingredients that was realized to facilitate Majorana fermions in such quantum wires are spin-orbit interaction, magnetic field, and an induced superconductivity in the wire. So the basic picture that one has for such a system is, okay, you have some spin orbit that's perpendicular to your applied magnetic field, which induces a Zeeman splitting in your wire. And then additionally, you have usually a superconductor that couples to the quantum wire, and this gives you a superconducting gap that's induced in the quantum wire. And the condition for achieving a topological section of the wire is that the square of the Zeeman splitting has to be greater than the square of the superconducting gap plus the square of the chemical potential in that area. And essentially, if you have an interface of a topological section with a non-topological section, then at the boundary of that interface, you obtain Majorana fermions. And these are basically zero energy states who particle is their own antiparticle. So there have been quite a few experiments to try and see these states, and the way that one probes these states is essentially a setup like this. So this is, I think, the first experiment that was done. Several experiments have followed, and essentially what you have is a quantum wire, and on one end you have it connected to, or you have put it on top of a superconductor, and on the other end you put it on top of a normal metal and apply a magnetic field, and then look at the conductance through your system. And so they all kind of have very similar data. Basically, this is a graph of the conductance. Here's the bias the voltage, and most importantly, one wants to look at the zero bias conductance. And essentially, what one sees is that as you increase the magnetic field, so going up along these lines, you see a peak beginning to appear as you increase the magnetic field at zero bias. And essentially, this is regarded as a signature of going into the topological phase. So basically, a Majorana appears, and you can have transport through this zero energy state. So more recent experiments were done in the group of Charlie Marcus. And basically, there's a couple main differences in these experiments. Okay, one big difference is that instead of on top of you have your quantum wire here, but instead of putting it on top of a superconductor, you coat part of it in aluminum. And when you can cool it to sufficient enough temperature, the aluminum becomes superconducting, and then you have proximity-induced superconductivity in the wire. So in this picture, you have one lead and another lead and a bunch of these things which are gates. And this blue part is covered in aluminum, so this blue part is going to be superconducting, and this teal part is not. And also, in addition, there is this part right here, which is indicated by this little white marker, and this is actually a quantum dot. So in this system, what they actually have is a kind of topological superconductor connected to a quantum dot. And they actually get some very nice results. First of all, they have a hard gap, which you can see here. And second of all, as they increase the magnetic field, they see a zero bias conductance peak, like in the previous examples. So it seems that quantum dots are actually useful for the detection of Majoranas, but it turns out they are also useful for quantum computation. So I will give you a proposal of one way that they can be used to facilitate topological quantum computation. So first, just a brief overview of what is a topological qubit. So to make a topological qubit formed from Majoranas, then what you need is 4 Majoranas. And one way you can have 4 Majoranas is have 2 topological superconductors, like this and like this. And the Majoranas on each topological superconductor can either be occupied or unoccupied. So one basis for your qubit is the so-called odd parity subspace, because there is one total kind of fermion in the system. And the 0 is defined as the left topological superconductor having their Majorana fermions being occupied, And the one state is that the right topological superconductor Majoranas are occupied. So this basically facilitates your basis for a Majorana qubit. However, it is not known how to perform universal topologically protected quantum computation on such Majorana qubits. So what people often do is they have to come up with schemes to facilitate these additional gates to achieve universal quantum computation. So we came up with a scheme last year involving a quantum dot. So in our case, we basically have two topological superconductors, one here and one here. And this basically forms a topological quantum bit with Majoranas. Then this is coupled to a quantum dot here. And this quantum dot is basically a spin qubit. So it's a two-level, in principle, non-degenerate system with some on-site interaction. And okay, the Hamiltonian of the quantum dot is given by this. And in principle, we allow for some overlap of the Majorana fermions. So the Hamiltonian describing the Majoranas is given by this. And we allow these two systems to couple. So the Majoranas can jump to the dot, and the electrons on the dot can jump to the Majoranas. So what we essentially did is performed a Schreiber-Wolff transformation on this tunneling Hamiltonian, and you get an effective exchange. Hamiltonian between the spin qubit and the topological qubit. So here, sigma 1 is the polymatricity that acts on basically spin space of the up and down qubit states of the spin qubit, and eta 1 acts on 0 and 1 qubit states of the topological qubit. And basically what this tells you is that these two qubits can entangle with each other. So one can perform a series of operations, like single qubit operations, and you can show that you can actually operate a so-called swap gate between the spin qubit and the topological qubit. So what that allows you to do is coherently transfer information between the spin qubit and the topological qubit. So the scheme then is following. Basically, you can't do all your topological operations. You can't do all your quantum computational operations on your topological qubit. So what one can do is store your information in your topological qubit because it is robust against decoherence, topologically robust against decoherence. You can perform your swap gate, transfer the quantum information into your spin qubit, and then perform whatever gates you need to do on the spin qubit, and then swap it back into the topological qubit for storage. So essentially what this allows is for you to achieve universal quantum computation, although not topologically protected, but using Majorana fermions. And it's facilitated by, again, this quantum dot. Yeah, that's one idea. I mean, basically, you can come up with whatever scheme you want, but in general, that was what one idea that we had. So, in general, yeah, I mean, you need to facilitate the gate somehow. So you can also perform braiding operations if you have the correct geometry to on your Majoranas. You can. I mean, you have to braid basically between. You have to braid. I mean, if you want to perform a braiding operation, you have to braid, for instance, like this guy across this guy. No, I mean, it's not enough. So the point is that in order to get all the operations, you can't just braid. It gives you a gate, but I don't think it gives you a sufficient gate. Yeah. Yes, something like this. So basically, it's like the dephasing due to the additional supplementary gates. So for instance, for us, we would have to we connect these two things together. We let them couple to each other, and there's some dephasing associated with letting the two things couple to each other. Yeah, you mean like quasi-particle poisoning or something like this? Yeah, there are these things. Yeah, this is one worry. look, there's a lot of problems with I would say, in general, like achieving a topologically protected quantum gate. That's why people have not done it before. I would say there's a lot of issues that probably go beyond our proposal, like the like not having a hard gap, things like this. You know, this tends to get destroyed when you apply a large enough magnetic field, and so I think there's quite a few problems. And as you said, quasi-particle poisoning, these can be problems. Right. So that's basically the idea, and what we showed is that taking basically one of these topological superconductor spins, or topological qubit, spin qubit hybrid structures, you can kind of connect them together into a network, and you can kind of get a nice scalable network that's amenable to the so-called surface code. So basically the point is that each of these little atomic sections can be scaled to some big network. And there was also so this is one proposal, and there was a similar proposal by Kartzig et al., which also used qubits and Majorana fermions to facilitate universal quantum computation. Okay, so that was kind of more or less just motivation. So I guess I wanted to motivate the fact that it's important it can be useful to couple quantum dots and Majorana fermions together, both in experiment and theory. And the question is, what exactly is the coupling between the Majorana fermions and the quantum dots? So as before, I kind of introduced a Hamiltonian that looks something like this, a tunneling Hamiltonian between the Majoranas and the electrons on the quantum dot. And there's some matrix element between the two, this T sigma. And in general, it can be spin dependent. And the question is, what is this quantity? Is it actually spin independent, and what variables does it depend on? And so essentially what we're going to do is calculate it analytically and numerically. And the way that we're going to do it analytically is calculate the wave function of the quantum dot and the Majorana fermion, look at the overlap, and then that will tell us T sigma. In addition to that, we'll consider the effect of two Majorana fermions and see if that changes anything, or see if it can tell us anything about, for instance, a Majorana fermion qubit. And then we'll do the same, basically the same thing using a type binding model, a numerical type binding model. So our setup is basically this to calculate our wave function. So we have a spin orbit along the z-axis, and a Zeeman, a magnetic field along the x-axis, which induces a Zeeman field, a Zeeman splitting. This is our quantum wire. Here is the topological section. Here is the non-topological section, and within the non-topological section, there is a quantum dot. And we consider the quantum dot to be some distance L away from the edge of the topological section of the wire. So what we focus on first is the Majorana wave function. This is what we're going to calculate. And the Hamiltonian that we take is given by this. So there is some kinetic term H naught, a spin orbit term here, a superconducting term here, and a Zeeman splitting here. And here are the details of the Hamiltonian. And the way that we go from the topological to the non-topological section is by changing the chemical potential. So on the topological side, it's given by some u sub t, and on the non-topological side, it's given by some u sub n. And this allows us to go from topological to non-topological sections. So it turns out you can solve the wave function of the Majorana. So in the large spin orbit energy limit. So what we consider is that the chemical potential on the topological side is equal to 0, and that delta z is greater than delta s. So this is really the topological. This is really in a topological regime. And then furthermore, that this mu sub n is actually mu sub n squared plus delta s squared is much greater than delta z, or greater than delta z squared on the non-topological side. So in fact, well, this guarantees that the left side is non-topological. So we solve for the Majorana wave functions, which one can do, and I'll spare you the gory details of what the wave functions actually look like, but I'll just give you some characteristics of them. First of all, on the topological side, it's basically a sum of two terms, and one term has a decay length given by the topological gap and has no oscillation in it. And the other term has a decay length that's given by the superconducting gap and oscillates with 2 times the spin orbit wave vector. On the non-topological side, you basically have, okay, there are two terms, but both of the terms decay with a length that's given by the superconducting gap, and oscillate with 2 times the spin orbit wavelength. Yeah. Say it again. This oscillation. So it's the spin orbit interaction that produces this oscillation. Suppress the oscillation. I guess probably you will. So the reason that you have this. So are you talking about in the square of the wave function or the wave function itself? So this is basically a picture of the square of the wave function, roughly. If you want to suppress this, you can. So basically, because it's like the reason that you have this oscillation is because it's a sum of two components that have different oscillation rates. So if you can suppress one of the components, then I guess the square of the wave function will not have an oscillation. Okay, so that's basically the wave function of the Majorana fermion, or the Majorana. And so now we look at we try and calculate the wave function of the quantum dot. So what we do to calculate this is we assume that the dot is fully depleted, so there's no superconducting correlations in the dot, just to make things simple. We take a parabolic environment, and we consider 2 limits. In the first limit, we consider the size of the dot, L, big L, is much, much smaller than the spin orbit length. And in this case, your Zeeman energy dominates, and you can neglect your spin orbit interaction. And you can also consider when the size of the dot is much, much greater than the spin orbit length. And in this case, the Zeeman splitting is exponentially suppressed. So you can basically solve the wave functions, and in both cases, you get basically like a Gaussian envelope. And in the small dot case, there are kind of no oscillations to the wave vector, but the energy levels are split by the Zeeman energy. And when the dot is large, you have kind of oscillations in this wave function that oscillate with the spin orbit wavelength. And furthermore, your states are more or less degenerate. They're exponentially suppressed by the ratio of the size of the dot and the spin orbit length. So now, basically, all we have to do is just calculate the overlap of the 2 wave functions that we found, and this will give you the up and down tunneling matrix elements. And this is the result that we get. So in the small, you can get an analytic result in both the large and the small dot limit, but you get particularly nice results when the dot is small. And this is what you find. And okay, the salient points about these 2 things is, first of all, that T up is different from T down, which, okay, is not, a priori you did not expect. And the way that they kind of principally differ is that they differ in phase by pi over 2. Second of all, as the dot moves away from the edge of the Majorana fermion, it decays with a length scale given by the superconducting gap. And lastly, that they oscillate with 2 times the spin orbit wavelength as you change the distance between the dot and the Majorana fermion. I think this is sufficient. Are you talking about this? Yeah, Bardeen. Yeah. I think this is also an okay. Mm-hmm. I don't have any details with regard to this Bardeen transfer. Is this what this is called? This Bardeen transfer method? Yes. Yeah. I recall this, and I'm not sure. Could be. Yeah. But yeah. Roughly. Yeah. Yeah. I mean, there's not so many quantitative features that we can say, but I mean, basically, it's kind of just some toy model that we want to, that will in the end compare to the numerics and see how closely it matches. I can show you. Well, I'll get to it. Yeah. So basically, okay, as I said, you have these oscillations, and they differ by pi over 2. And you can play the same game for a large dot, and you get roughly the same thing. You just have you have a different rate at which the T sigmas oscillate. And kind of what's interesting or useful or not useful, but let's say of note about this is that if you, as you change the distance between the quantum dot and the Majorana fermions, you actually tunnel the ratio. You can change the ratio between the up and down tunnelings. So you can go anywhere from something that's totally spin polarized transport to equal spin independent transport. So that's basically the single Majorana case. But now we consider a Majorana, a quantum dot sandwich between two Majoranas. So in this picture, we have a Majorana on the left and a Majorana on the right, both of which are the same distance away from the center of the quantum dot. So here you have basically the same tunneling Hamiltonian, but you have a tunneling not only to the right Majorana, but to the left Majorana. And basically, these two Majoranas can form into a complex fermion given by this, and this state can either be basically occupied or unoccupied. So we go through kind of the same game that we played in for the qubit before, and we perform our Schreiber-Wolff transformation, and we get the following we get this tunneling Hamiltonian. This tunneling Hamiltonian turns into this, and here SI is the dot spin operator, and basically what this is telling you is depending on the occupancy of this non-local fermion, you get a different magnetic field or a different effective Zeeman field that the dot feels. So that is to say, when the non-local fermion is unoccupied, the dot kind of feels a effective Zeeman field of B minus, and when it's occupied, it feels an effective Zeeman field of B plus. So you can kind of go through and calculate it exactly, and it turns out that both B1 and B2 are identically equal to 0. And this comes, okay, you can show that that's true, but it comes basically from the symmetries that your system has. But B3 is non-zero, which is good. So first of all, you can show that it's non-zero, and second of all, you can show that B3 minus and B3 plus are actually different. So, okay, just graphing this function, you see that it looks like this. It has some exponential decay, and it oscillates with 1/4 of the spin orbit wavelength. And you can play the same game with a large dot, and you see that it basically has the same behavior, except it oscillates half as fast. And what's kind of nice about this is that depending on whether the this kind of non-local fermion state is occupied or unoccupied, just by measuring the effective magnetic field on the dot, then you can tell, so by measuring the effective magnetic field on the dot, you can tell whether this kind of non-local complex fermion formed from the Majorana fermions on either side of the junction is occupied or unoccupied. And this can potentially be useful for readout of topological qubits. So that was the case where the Majorana fermions were equidistant, were the same distance away from the quantum dot. Okay, if you make the dot a little bit closer to this side or a little bit closer to the other side, you actually break one of the symmetries in your system, and you see that you actually not only get a component along B3, but you also get a non-zero component of B2. Okay, and I mentioned this because it's going to be relevant for the numerics when I discuss them. So onto the numerics. Basically, it's roughly speaking the same exact, a very similar system. You have a topological section with spin orbit interaction and applied. So basically, you have spin orbit interaction and Zeeman splitting everywhere. And then in the topological section, you have a S-wave superconductor. It has proximity-induced superconductivity. And then a non-topological section, you have no superconductivity, and you consider it to be really depleted. and there you define a quantum dot. And then, of course, you have a Majorana fermion at the interface. Okay, so we can plot the wave functions and plot the energies just using the, you can plot these. And then what you see is that, okay, here's your quantum dot at site 30, and then your Majorana fermions live at the boundary between the topological section and the non-topological section. And here, when you look at the energies, you see that the Majorana fermions really sit at 0 energy, or pretty close to 0 energy, and that the up and down spin states on the dot are degenerate, which is what you would expect for a large dot, which this is. So, okay, so the energy of the dot when it's far away from the Majoranas is given by epsilon naught, and when as it gets closer to the Majoranas, it starts to hybridize with them. And so its energy changes according to something like this, where T sigma is actually the tunneling term that we calculated analytically in the previous section. So if you know that the way the energy changes, you can extract the this tunneling T sigma, and that's basically what we do. So as we move, this is just the wave functions of the Majorana and the quantum dot when they're far away from each other. So this is, I guess they're like 170 sites away from each other. So this is what we do. So we basically move our dot. Well, in this case, it starts out close and then moves further and further away. And by just looking at the energies, we can extract these T up and down. And we see, roughly speaking, oscillations in T up and T down with given by this with oscillations that are given by the spin orbit length, and that are some phase offset from each other. So it seems to have pretty good agreement with the analytics that we calculated. So next, we basically do the same thing except for a Majorana fermion, quantum dot Majorana fermion. Here again, you have a picture of the square of the wave functions. Majorana's here, quantum dot in the middle. And again, just to be complete, you have your spectrum here, so your Majoranas are still at 0 energy, and the levels of your quantum dot are degenerate. And basically, we play the same game. So the problem is you can't actually extract, or we couldn't figure out a way to really extract the Zeeman splitting from, yeah. 0. It's all 0. It's the same, everything's kept at the same phase. So we couldn't figure out a way to really extract, let's say, the Zeeman splitting in particular from the Hamiltonian after diagonalizing it. So the way that we kind of extract the effective Zeeman splitting on the dot is essentially by just calculating the total spin on the dot. And the way we did that is we just calculated the expectation value with the wave function on the dot. And we see essentially we get a component along x, which corresponds to B3, and a component along y, which corresponds to our B2. And for us, it was a little bit confusing as to why we had a SY component, because in principle, if it's really symmetrically placed, it should be 0, just according to the symmetries of the system. But it turns out it was not symmetrically placed. It's just slightly to one side. So in this case, we got a component along y and a component along x. Okay, I'm almost done. Right, so basically my conclusions. So the conclusions are that spin-dependent tunneling depends on the distance between the Majorana fermion and the quantum dot. And there's kind of advantages and disadvantages to this. So if you can really precisely define the distance between your quantum dot and Majorana fermion, then you can actually kind of use it to your advantage. You can kind of tune the ratio of the tunneling up and tunneling down to be kind of whatever you want. However, if you cannot so precisely define it, then you may get kind of unlucky. And if you're unlucky, then maybe it's totally spin polarized or equal spins or something that you do not want. And furthermore, you could be even unluckier. So if you really cannot define it, then it could be a potential source of error, which could lead to problems in your readout and problems with operations of your your topological qubit if you use a quantum dot to manipulate them. And second, the effective spin, the spin or the effective magnetic field on such a quantum dot coupled to 2 Majorana fermions could be in principle used to detect the state of a Majorana qubit. And lastly, this was recently put on the archive, and you can find the reference here. Thank you for your attention.
Thank you. What do you mean by this unlucky position?
Yeah, so sometimes like